I think you will be able to see. Anyway, so today we are discussing the equilibrium PP chain, PP1 chain. Okay. Now on this part you can see the three reactions, three characteristic reactions, where we start with the proton-proton fusion, right? And finally we get this 4 helium. So this is the overall result. And we start with this thing. So this is start. And this is the end result. And of course, this 4 helium and this 3 helium later on, this can be also used to start the pp2 and pp3 chain reaction. And also this helium 4 is also used. Anyway, we have talked about this. Now today I would like to talk about the reaction rate for these equations. So you see the corresponding rate equations I have shown on this part of the diagram. Now you start the understanding from the below. So what is this here? H, D is basically 2 hydrogen, right? Deuterium, 3 helium, 4 helium. So they are basically the number density. Now let's start with the bottom. So what's the number density for helium? Time rate of change. Here, look into this equation. You see the production of helium is entirely due to these two, right? 3 helium. So we can write this as 3 helium square, half into the lambda factors as well. Now next you consider the case for 3 helium. So this case over here. Now what you see over here is that the 3 helium which is produced, it is somewhat used up in creating 4 helium. So you will get a minus sign over here. So because this is being used up, right? So minus lambda 3 for 3 helium, and this 3 helium is being produced as a result of this reaction between deuteron and proton, right? So this you will have a positive sign here, and this is being consumed, so negative sign. Okay. Now next you consider the case for deuteron. Again, the same thing happens. Deuteron is being consumed by this reaction, so there will be a negative sign. You see, corresponding to the proton and deuteron, so consumption, minus sign. And next, in the first line over here, it is being produced. Deuteron is produced by this reaction, so we will have a plus sign over here. Lambda pp a square by 2. ठीक है? Okay. Now finally, this part over here, that means ddt of the number density of proton or hydrogen, right? এবার দেখো এখানে কোথায় কোথায় তৈরি হচ্ছে, where is it being produced? Here, you see, this is being produced over here. So you will get a plus sign because of this, plus sign because of this. Why? Because this is produced as a result of consumption of this 2 helium, right? So you will get a plus sign as a result. Next, দেখো এখানে আমার these protons are being used over here, right? So we will have a minus Hd term, and also in this term also. In these two parts, the proton is being used, hydrogen is being consumed. So correspondingly, we will have 2 negative signs. And so we will get these 4 rate equations corresponding to the pp1 chain reaction. ঠিক আছে? এবারে I would now like you to check whether the barrier number is conserved or not, and this will be a homework. ঠিক আছে? We will start from this part next class. বলো, barrier number. This is the barrier number. You can check for yourself. Okay, so we were considering the equilibrium pp1 chain, and before I proceed with the with discussion on that, let me first recapitulate this thing. You must remember that we have already considered, we have already derived the reaction rate equations. And this I have derived when I was considering the composition equations, right? When I was deriving them. And now you see we have got two different forms, one for non-identical case and another for identical case, and this I can write in a compact form together using this delta function, Kronecker delta function, right? Now okay, so this we can write. Now you see this is what we have considered in our classroom. Okay, so we were considering the equilibrium pp1 chain, and this is the 3 pp1 chain reactions. So you must be wondering that what is it that we really want to investigate here. Basically what we want to investigate is the following. Basically we would like to investigate how the deuteron and 3 helium abundance evolve in this pp1 chain. And this is why I have considered, you see, the rate equations I have written, and you must remember I have already described this in the classroom. Okay, now what is this lambda pp? Basically, as I was just telling you, this we have already derived when I was considering the composition equations, right? Now you see this lambda pp is basically this sigma average part over here. You see, when I am writing this in a compact form, the number densities of the two species, they are coming out, right? And so we have the average over sigma into V divided by this term. For non-identical case, this is 0. For identical case, it will be 1 plus 1 equal to 2, as you can see over here, right? So basically, in this particular equation, this H is basically number density of hydrogen. Similarly, this D is basically number density of deuteron, right? And so what is lambda pp? Lambda pp is basically sigma into V pp. What is lambda into D? Lambda dp is basically again average of sigma V for the PD case. Okay, so this is what we have already discussed in the class. Now I already asked you to do this problem, remember? So I asked you to really show that the baryon number is conserved, right? So I asked you in the classroom, and you see, for that you just have to do this. You just have to take the time derivative and show that this is equal to 0, and this is what is done over here, you see. So basically I told you that this is the baryon number, this term, right? So this is the baryon number, right? Now if I do the time derivative, then I'll be using this set of equations here for the time derivative, and you can check for yourself that of all these terms they cross each other, cut each other, and we finally get this ddt of baryon number equal to 0, basically, which means baryon number is conserved. Okay, now let's move on. So this is our first scenario, first important discussion regarding this. Now let us assume that deuteron is in equilibrium. So deuteron is in equilibrium. Then what will happen? You see, when deuteron will be in equilibrium, then what will happen is that we will have basically ddt equal to 0, right? Or basically I can write like this. So basically, and you will see that this equation, so basically this, and from this equation you will see what we have. Okay, so cutting the part of H, you will see that we get this equilibrium deuteron abundance. So this is basically the equilibrium deuteron abundance. Fine. Now if we substitute this result in the other equations, then what we will get is this. So this is the form of the rate equations, right, when deuteron is in equilibrium. So these are the form of rate equations when deuteron is in equilibrium. Of course, we have to add, since deuteron is in equilibrium, so ddt of deuteron concentration is equal to 0. Fine. Okay. Now we will move forward and consider the case when 3 helium is in equilibrium. Right. So when 3 helium is also in equilibrium, then what? Again, since this is in equilibrium, so ddt of 3 helium is equal to 0, and from the rate equation we can write this one, right? So this is what we obtained when deuteron was in equilibrium. Now we will use this equation and we will put this equal to 0, right? So this is what we get, and this will give me the equilibrium abundance ratio of deuteron with respect to hydrogen. This one, you see, just from this. So this is basically the equilibrium abundance ratio of 3 helium with respect to hydrogen. Right. Now again let us substitute this into the remaining equations, and then what we will get. See, so these are the form of the rate equations when both deuteron and 3 helium is 0. Of course, this means that dt equal to 0 and ddt of also 3 helium is equal to 0 along with this, but this is needless to say. Anyway, okay, now you see, let us concentrate on this equation over here. Now you see, from this equation it follows that the time scale for change in the hydrogen abundance due to equilibrium pp1 chain is basically given by this tau of h, which is defined like this: minus ddt of ln h to the power minus 1, and this value from this equation, it gives me this value. Now since we have already obtained this, so basically we have obtained a time scale for change in the hydrogen abundance due to the equilibrium pp1 chain. Let us now try to estimate. Okay, so this is our last work. So let us try to estimate estimate the time scale for 3 helium to come into equilibrium. Okay. Now for that, suppose, let us start. Okay, so suppose the 3 helium abundance differs from its equilibrium by a small amount. So let us write like this, small amount. So I am writing like this. Now you must remember that we have obtained this relation, right? When I was considering the helium to be in equilibrium, so this we have just obtained, and we have now again written this along with this small change, epsilon. Fine. Now we will start with this form, this equation, when D was in equilibrium, right? So let us expand this. So let us expand this equation around the equilibrium value, right? Which means this one, this concentration. And as a result, we will have, so you see, the result is the following. This one, ddt, with the equilibrium value plus the small change, and this gives me this result. And now let us rearrange. So rearranging, I will get this value of ddt of epsilon. Now you see, we know that the value for lambda pp and lambda 33 are given by this. And in general, basically, as you can see, the value for lambda 33 is much greater than lambda pp. And as a result, this last term is negligible compared to the first term. So this means third term is negligible compared to first term of RHS, right? Also, let us drop the second order term, which is this one. So we will be left only with the this expression. So neglecting second order term epsilon square, we get, so this is what we get from the previous expression, and this basically gives me this tau 3, which is basically the 3 helium time scale, right? So this is what we wanted to find. Okay, so now let us graph the ratio of time scales tau 3 by tau h for temperatures, say T6 is equal to 1 to T6 is equal to 20, and see what happens. So you see, this is the result, and from this part what you can say, basically the assumption that 3 helium is in equilibrium, it is not valid for all temperatures. You see? So this graph tells us that 3 helium comes into equilibrium before hydrogen has changed significantly, only if this point, only if you see the temperature is around, say, greater than 5 into 10 to the power 6 Kelvin. So this means that the basic assumption that 3 helium is in equilibrium, this is not valid for all temperatures. So assumption that 3 helium is in equilibrium is valid is basically not valid, right, for all temperatures. Only in this case we can have this scenario.